Newton's three laws of motion since fall break, and this is the last of the three. It is the one that most people know the wording of, or at least something similar to it, but have a very bad fundamental understanding of it. So let's start in here with just the wording. For every force, there's an equal and opposite force. Now, some word it as for every action, there's an equal opposite reaction. And I don't really like wording it that way for specific reasons. You could say for every action force, there's an equal and opposite reaction force. And that's fine. But to say that for every action, there's an equal opposite reaction is not true when most students think of what their reaction is to something. So a couple things that we want to talk about first before we get into that more is that forces always act in pairs. Your weight is caused by the earth pulling on you with its mass through the force of gravity, but you also pull back on the earth. All right. Even though that the earth is huge, all right, and you're small, those forces, all right, are always equal. All right. They're just in the opposite direction. I'm pulling up on the earth is pulling down on me. These interactions with something pulling on something else or pushing on something else, those forces are always equal, just opposite direction. And there are no exceptions to this. It doesn't matter how big or small the objects are. So let's get into a few examples to go through this idea of Newton's third law. So here's the first practice problem that helps draw out some of the misconceptions students have. Let's imagine we have a heavy football player and a light one running at each other. The light one is got the football and they're running towards the goal, and the heavy football player, they are the defense running at the guy with the football. And as they run towards each other headlong, they have this collision. All right. Who experiences the greater force? Well, Newton's third law states that they are equal. Have to be. There's no exceptions to that rule. As the small football player hits the big one hits the small one, and they have to be equal. All right. So they experience the exact same force. All right. Now, this is not what most students would want to say in their gut. They want to say that the big one hits. All right. And the reason for this, again, is because when you hear that original phrasing of this, for every action is an equal opposite reaction, most of the time students think that as the acceleration, the reaction to the force. You hit something, it reacts, all right? And the reaction to those equal forces are not going to be equal. Right? So that reaction, okay, of the heavy, more massive player is different from the reaction of the lighter mass. Obviously, those reactions aren't the same. The big guy is not going to jolt back nearly as much, where the light person is going to have a huge acceleration, very big reaction. So the question there is why? All right. What's going on there? Well, this gets back into Newton's second law. All right. Those forces are going to always be equal, but the reaction to those forces is based on the mass. Newton's second law clearly states that as the mass, that acceleration is inversely proportional to the mass. So, in other words, as the mass increases, the acceleration gets smaller. As the mass decreases, the acceleration is going to get bigger. All right. The same force was exerted on both of those players. It just has a different reaction. So that's why we worded in this class, for every force, there's an equal and opposite force. Let's try another. High-speed bus moving along, smashes into a bug. All right, the bug gets splattered all over the windshield. Is that force pair, the bus hitting the bug hitting the bus, how do they compare? Well, they are the same. Has to be. Right. The resulting acceleration or the reaction to that force, obviously, the bugs is much smaller. The bus does not slow down in any measurable way. So let's actually apply this to what we've been working on here lately with force diagrams. Let's imagine we have a cannon. That cannon has a mass of 1,000 grams, or kilograms, excuse me. That's firing a cannonball with a mass of only 10 kilograms. If that cannonball is fired with a force of 5,000 newtons, first off, what is the force acting on the cannon? Well, if the cannon is pushing on the cannonball with 5,000 newtons of force, it must be being pushed with the same force, just in the opposite direction, 5,000 newtons. So then the question gets into what's going to be the acceleration for those two objects. All right, so I have a cannon. All right, and I have a cannonball. Okay. That cannon, we'll do in blue, has got a force of gravity, a normal force, and also it's being pushed by the cannonball. The mass of that cannon is 1,000 kilograms, so that means there's 10,000 newtons of force here, 10,000 newtons of force here. And since it's firing the cannonball with 5,000 newtons of force, it also experiences a 5,000 Newton force. The cannonball itself is only 10 kilograms. So that means it has a weight of 100 newtons. Normal force of 100 newtons. But is being shot out with that exact same 5,000 Newton force. So let's go ahead and calculate. Again, if we are looking to find the acceleration of both of those, it will be net force over the mass. The cannonball, let's go with that one first. Net force on this is just that 5,000 newtons. So to find the acceleration there, it's 5,000 newtons over its mass. That mass is the 10 kilograms. So that means it has an acceleration to the right. All right, I'm just going to put an arrow there for to indicate 500 meters per second squared. All right, to the right. If I do the same thing for the cannon, its acceleration is going to be that net force of 5,000 newtons. Has a mass of 1,000 kilograms, so its acceleration is 5 meters per second squared, but this case is to the left. All right, this is why, if you've ever fired a gun before, you get that kickback. All right, you are causing a force on the bullet. The bullet is pushing back. Since the bullet has a much smaller mass, it accelerates rapidly in one direction, where you accelerate much less in the opposite direction because of your greater mass. And that's how Newton's third law applies to the situations we've been dealing with.